You might ask here, why, Mike, are you reviewing this stupid reaction? Well, as it turns out, once you have a bromine on the benzilic carbon, you can do lots of really useful things with it. As you may recall from Chapter 8, a bromine is a really good leaving group, which means that if I react it with a nucleophile, the nucleophile can displace and substitute itself for the bromine. Thus, the nucleophile comes in, attacks the benzylic carbon, kicks off the bromide as a leaving group, and takes its place. This type of substitution reaction is called an SN2 reaction. Here are various examples from section 16.1 of different substitutions I might do for my benzylic bromine. Foremost, I can react benzyl bromide with OH- hydroxide, which could arise from sodium or potassium hydroxide, for instance, to generate this product, benzyl alcohol. Alternatively, I can displace my bromide with a cyanide nucleophile to form phenylacetonitrile, as shown here. Or if I wish, I can use ammonia, NH3, as my nucleophile, and displace the bromide to form this ammonium salt. When this ammonium salt is neutralized with hydroxide, it then gives me benzylamine. These reactions are all extremely useful. I'd like you to show me how to arrive at any of these three products directly from benzene in a single step. Can you? Absolutely not. We have to go through a substituted benzene that's been brominated at the benzylic position. Another reaction we can do if we have a bromine at the benzyl carbon is an elimination reaction. Thus, by treating the brominated starting material with a bulky base like potassium or sodium tert butoxide, I can form styrene, shown here. This reaction is an E2 elimination reaction, which we covered back in Chapter 9. One cool thing you can do with styrene is to treat it with hydrogen gas and palladium, which will then reduce it to ethylbenzene. The humorous thing about this slide is that if you were to treat ethylbenzene with NBS and light, you would actually brominate the benzylic carbon and convert ethylbenzene back to our original starting material, 1-bromo, 1-phenyl ethane. Thus, converting 1-bromo, 1-phenyl ethane through this sequence to ethylbenzene in reality would be a stupid waste of time. However, it does illustrate the ability of doing an E2 reaction when you have a bromine at the benzylic position, thus forming an alkene. And as you may remember from previous chapters, there are many reactions that we can do to alkenes. Just to review, I thought I'd show you here the mechanism for the E2 reaction featured in the previous slide. Once again, I have my bromine bonded to my benzylic carbon, and my bulky tert butoxide base comes in and grabs a hydrogen that's on the carbon adjacent to the benzylic carbon. Upon doing that, it thrusts these electrons in, closing them like a door on a hinge, and kick off the bromide leaving group. This forms my double bond featured in styrene, along with tert butanol and bromide byproducts. I'm now going to move on to another reaction shown in section 16.1. This reaction is the oxidation of benzylic carbons. You see, if you have an alkylated benzene, and the benzylic carbon is bonded to at least one hydrogen, then you can react that compound with certain conditions to convert it into this product here, which is called benzoic acid. Interestingly enough, it doesn't matter whether these R groups in the starting material are alkyl chains of any length or branching pattern, or just hydrogen atoms as well. These conditions will convert any starting material of this type to the same product, benzoic acid. And what are the conditions? Well, they're the ones shown here. KMNO4 in water, or sodium dichromate. Thus, if you take any compound of this type, regardless of whether R1 or R2 are alkyl chains of any branching type or just hydrogens, it will convert this type of product into benzoic acid if treated with potassium permanganate and water or sodium dichromate. I do not want you guys to worry about knowing the mechanism for this reaction. Now, by comparison, if we use a milder oxidizing reagent, manganese dioxide, MnO2, it will only oxidize a starting material up one oxidation state to this type of product. So if this, for example, this R group were an H, then what I have is my starting material's benzyl alcohol. If I treat that with manganese dioxide, it will oxidize it up one bond to benzaldehyde. If by comparison this is an alkyl chain, then this is a secondary benzyl alcohol. It will be oxidized up to the ketone shown here. Manganese dioxide will only work if you're starting with a primary or secondary alcohol. So let's move on to some actual problems. I want you to predict the products of each of the following reactions. Because I'm going to discuss the answers to these problems on the next slide, this might be a good place for you to pause the video and attempt to do them first on your own. So here are the answers. Whenever you see an alkylated benzene being treated with KMnO4 water or sodium dichromate, it doesn't matter how branched the alkyl chain is. All you have to do is ask yourself one question. Is the benzilic carbon bonded to at least one hydrogen? So I'm going to ask you that question for this first example. Is the benzilic carbon right here bonded to at least one hydrogen? Well, the answer is yes. So if I take this starting material and react it with KMnO4 water, what product does it make? Benzoic acid. Let's take a look at this benzyl alcohol. You might remember that manganese dioxide is not as reactive of an oxidizing agent as KMnO4. So if I take this benzyl alcohol and react it with manganese dioxide, what happens? Well, it only goes up one oxidation state, or one bond to oxygen, to make this product, benzaldehyde. Let's look at our next starting material, this isopropyl benzene. If I treat that with sodium dichromate, what product is it going to make? Well, all I have to do is look at this benzilic carbon and ask the question, is it bonded to at least one hydrogen? The answer is yes. So what product will it make? Benzoic acid. This same product would be achieved if I took this same starting material and treated it with KMnO4 water as well. Now let's look at this starting material, tert-butylbenzene. Is there a hydrogen bonded to the benzilic carbon? The answer is no. So if I treat it with KMnO4 water or with sodium dichromate, what will it do? There will be absolutely no reaction. This, I think, is a great place for us to stop our video from Chapter 16. Please take a break, get some snacks, go to the bathroom, or do whatever it is that you need to get recharged. Then return and watch the next video segment to continue with Chapter 16.